So far in this course, we have learned how micro devices are made. We learned a little bit about how they behave under static and dynamic conditions. And now the third topic that is going to be discussed in this course is how is information, let's say, exchanged between different physical domains. So that's called transduction. And this is basically the last topic we need to know before we can complete the modeling aspects for a micro device. So in most situations, in most cases, what we have is an input to a system and we monitor the output. In many situations, we have the ability to look at the input and output, and the idea is to come up with a model that represents the response of that system, right? This model, we go through that in a second, can be put together in different ways. In microsystems, situation is a little bit more complicated, or we can break it into a few more pieces here. The input can be coming from a certain physical domain. It could be a temperature change in the environment, or it could be an actuator that you're applying a, let's say, electrical signal to it to move, right? And then what happens is that you have a transducer that converts electrical information into a mechanical displacement, so electrical to mechanical conversion. Then you have a mechanical system here that now sees a force that is proportional to your electrical signal, responds to that force in a way that is, determined by its, let's say, dynamics. And then at the end, I have probably a system that monitors the displacement, right? So I go back from mechanical domain to a domain that I can understand using my microprocessors, usually electrical. So mechanical to electrical conversion again, and this goes to an electronic system, right? So it could be a change in capacitance that my circuit measures or things like that. So there are a few components here. I have conversions between or exchange of information or coupling of energy between different domains. Now, the modeling, therefore, can be quite involved. So when I'm considering a problem in microsystems, I have to establish context, right? What is it that I want out of this model for this problem, right? So for example, you may be looking at an accelerometer, and in this case, your response, let's say you want something that is responding to DC signals, fairly low frequency. And we saw from the dynamic analysis before that if you're looking at slow changes, you really don't have to worry about dynamic response. The damping in your system. However, similar device, if I'm interested in vibration measurements instead of acceleration measurements, then I may not really worry too much about the DC response. I care more about the dynamic response of this device and how it responds, and maybe even damping is going to be a very important issue for me. So I need to establish context. What is it that I'm going to model? What is it that I'm interested in? Because if you do not create those boundaries, the model can be just too complicated. I define parameters, constraints that I have for my parameters, and the level of accuracy that I need from that model, right? If it is a model, back of the envelope calculation, and I'm targeting a 10% accuracy or 15% accuracy, that's all good. But if I want to get to 1% accuracy in terms of the system response, then I probably should start with the model on the back of an envelope, but go and refine it using numerical analysis or more advanced tools. I need then to design a proper model. It could be physics-based, right, based on all those equations that we've seen so far. And it's all good. In most cases, if you do the problem, the analysis at the beginning properly, if you put together the model properly, the boundary conditions, equations of motion, all that, these models can get you within 5 to 10% of the true levels, true responses of a system with relatively little effort, right? So I'm going to say relatively little effort. That's true for relatively simple situations, right? So if you have beams of varying cross sections and let's say materials with anisotropy in them and all that, things become too complicated to to be handled using a physical model, we usually have to go and use numerical models. Numerical models can take into account complexity that is hard to model using physics-based models, closed form expressions, like, dealing with an anisotropic material, for example, could be one of them. And they could also take into account the interactions between different physical models more easily. You can model that more easily. However, remember that if you do not put together your numerical models carefully, they can show you some response and it can look pretty and colorful and nice, but it could be totally wrong. So just to make sure that your numerical model is working properly, the numerical simulations are doing their jobs properly, you usually start with a physics-based model. It could be very simplified, it could be much simpler than it is needed to get the accuracy that you want, but you use that and look at how the system should respond, and then you look at the numerical output, so that you do not just believe the output of any numerical simulations just because the computer said so. And then nowadays we are using more and more these statistical models. These are models that can actually account for unmodeled complexities, right? You could have complexities in your system that you do not have a proper physical model for it, and your numerical simulator may not be able to account for those things as well. Sometimes you may not even know why the system is responding in a certain way, but it is a repeatable response. It is not noise. It is just behaving that way all the time. And in those cases, you can use the statistical models. You basically create a model of the system that is not based on the physics. It's just based on how the output changes when you apply an input. And then the system in these cases may be a black box to you. Again, you have to use these models very, very carefully. You now know even less about what is inside that black box compared to a numerical model. And therefore, if you're not carefully setting it up, it can just give you a wrong response, and you shouldn't really believe the model output without having some faith in the response, right? So you have to know the answer before you can trust it. And that can come from your physics-based or numerical models. At the end of the story, you want to evaluate your model, right? So numerical evaluation is cheap and you should always do it. And then physical evaluation is when you go and test the device in a lab, in a proper test environment, and you look at the response of the system to see how it behaves, compare it to the model output, and then if needed, you have to go and revise your model. Now, what is a transducer? A transducer is a device that converts the changes in one physical quantity into changes in another physical quantity, right? So it is basically sitting in between two physical domains, and at microscales, this can happen in a variety of ways. So for example, you can have piezoresistive transduction, where the resistance, electrical resistance of a material or a device changes in response to mechanical stress. So it is coupling mechanical and electrical domains to each other. You can have electrostatic transduction, where an electrical signal is converted into a force, which can move structures for you. You can have piezoelectric transduction, where a mechanical stress produces a charge, electrical charge, that you can measure. Or you can apply a voltage to this, or an electric field to this piece of material, and you will see a mechanical deformation. Thermal transduction, you can have a thermocouple where a heated end produces a voltage at the other end, at the cold junction. Or you can have a thermal actuator where you pass a current through a beam and it expands and it moves something for you. So the thermal domain, electrical domain, and mechanical domains are coupled. Magnetic transduction, where a magnetic field, for example, produces a voltage on a Hall effect sensor. Optical transduction, where you can use light to move stuff at these scales, for example, and so on and so forth, right? There is a lot of different transduction mechanisms, and when you're dealing with a microsystem, you have to know which ones are dominant, and you have to know if there are some interfering issues from others, right? So for example, if you're designing a piezoelectric device, you want to make sure that your electrostatic interaction is minimized or let's say well controlled. Or if you have a piezo resistor to measure the stress on a structure, you want to make sure that you're not heating up that piezo resistor by passing the current through it. Because if you heat it up, you get thermal effects or electrothermal effects, and that can interfere with your measurement. So you either avoid the interaction that you don't want by setting up your test properly, or if that interaction is unavoidable, like a piezo resistor that is heated, you need to include that transduction in your model as well. If you are making a sensor, there are a bunch of parameters that people use in order to specify the performance of a sensor. So here is a typical response that you have an input signal and your sensor is producing a signal proportional to that input. Sensitivity is basically the derivative of that input-output curve, the characteristic curve for your device. How much does the output change if I change the input for a given amount? So the slope of that curve is your sensitivity. Resolution is the smallest change at the input that you can measure, right? So for example, if you're using a temperature sensor, what is the smallest temperature change you can measure with that sensor? And it's often limited by noise in your system from the mechanical side, electrical side, or optical side. Dynamic range is the difference or ratio, depending on how you define it, between what is the largest signal you can measure with this sensor and what is the smallest signal you can measure with this sensor. So the smallest side is usually your resolution. It's limited by noise. The largest signal is usually limited by some physical limitation. So it could be the power supply that you have available to you. You cannot go beyond the power supply if it is a typical linear sensor. Or sometimes it's non-linearities that kick in and limit the amount of signal that you can get at the output of your device. You will start to deviate from a linear response, you cap it, right? So you see, 1G is the maximum that I'm going to measure with this accelerometer because its response becomes non-linear. So dynamic range is the ratio or the difference between the largest and smallest values. Accuracy is about how true the value that you read at the output of the sensor is. In other words, how close is the output of that sensor to the true value? So if I measure this with an ideal, let's say the temperature in this room, if I measure it with an ideal sensor that is well calibrated and has no error in it, and it reads some value, and I read it with my cheap sensor here, how close is that value to the response from this ideal sensor? Precision, on the other hand, is about repeatability. So if I measure the temperature in this room 100 times, how much variance do I see in that temperature, right? So what people usually do they say, let's say this is, well, you have to look at it on a linear scale, but I'm going to show it in a 2D scale for clarity. Let's say the true value of some variable is this. And I use a sensor, and I start to measure values that look like this. So I measure the first response, and it's going to be this. The second one is this. The third one is this. The fourth one is this. Fifth one is this. And sixth one is this. So that's the response from one sensor. I use another sensor, and I get readings like this. So the first one is this, the second one is this, the third one is this, the fourth one is this, fifth one is this, sixth one is this. So these are the responses from two of these sensors. Accuracy is about how close the values are to the true value. So between these two sensors, well, this one is giving me a more accurate reading, right? The red one or the circular ones, because they are closer to the true value. But the second sensor, the one that produced this group of values, is more precise. The readings from that sensor are tighter, are closer to each other. So even though it is not as accurate as the first one, it is giving me a more, let's say, repeatable output, reliable in terms of repeatability output. Ideally, of course, I want a sensor that is both accurate and precise. However, those sensors are going to be very expensive. So I usually have to sacrifice a little bit of precision or accuracy in most typical situations. Offset is the non-zero output of your sensor even though your input is zero. So you've seen this for electronic systems. You know, your op-amps had offset voltages, a few millivolts, even though the input was zero. Sensors can behave the same way. In many cases, that offset is due to some systemic asymmetry in your system at your MEMS level or electronic level, but it usually not easy to cancel it. You know, you have to just deal with it in some other way. Linearity is, you know, how true or how well are those measurements for different input amplitudes lie on a straight line, right? And then any deviation from a straight line in terms of input-output characteristic curve will be an issue of nonlinearity. Drift is how stable that the sensor output is over time. So if you look at the sensor output, and if nothing changes around this sensor, without any change in the environment, you will see a little bit of a change at the output of that sensor. It could be due to different effects like aging, like all sorts of problems that may not be easy to model, but in most cases there is a little bit of drift in the output of your sensor due to events that you cannot really easily model or rule out. Response time is basically how much time is needed for your outputs to reach its final value, basically how much time you need to wait before you should read the sensor output and make sure that it is stable. And bandwidth is, you know, for this sensor, what are the range of frequencies of input that it can respond to. And usually we define it by 3 dB corner frequency. You know, we discussed that before. Sensor bandwidth is also an indication of its response time. So the two are related. Not exactly the same quantity. It's not, you know, F3 dB is not 1 over tau, but they are related to each other. Now, if you want to use a transducer as an actuator, you usually deal with a different set of parameters or performance requirements. For an actuator, it has to do work for you. So one important parameter is the continuous output power, right? So if I want to use this actuator to keep moving, let's say, a meter back and forth, how much can I expect from this? What is the maximum or expected output power that I can get from this device over a long term? Peak force and torque may also be important, right? So if I want to apply a large amount of force and then maybe go back to a dormant state, how much is those peak force and torques? And the reason that it is different from continuous power, output power, is that, you know, you usually have to account for the losses in your system. And if you have a continuous output, if you keep moving something back and forth, you normally produce some heat. You have to be able to get rid of that heat in your system somehow, or otherwise the temperature in your system keep rising up. If you are doing something over a very short amount of time, yes, you may produce a lot of heat, but then you're not doing anything, and that heat has time to dissipate. So the peak force or torque can be much, much higher than the continuous amount of force or power that you can get. Range of motion is similar to dynamic range for your sensor. You know, how much is the linear or rotary motion that I can get out of this actuator. Resolution is the minimum amount of displacement that I can get or output that I can get at the output of this actuator. Why do I have a minimum? Well, sometimes these actuators are interfacing with, let's say, a D2A. So are limited by the steps that are imposed onto you by the D2A. But there could be other situations where your actuator is actually moving in a stepwise kind of a response. Accuracy is similar, how reliable, when you say, I want this to move by 1 micron, if I apply 1 volt, do you really get 1 micron out of it, or you're getting 0.9 microns? Something like that, right? Heat dissipation is an issue, especially if an actuator is continuously operating, you're switching the mirrors back and forth, or you're using a thermal actuator to move something. So you have to make sure that you're not raising the temperature of the system. For actuators, speed is also important, right? So sometimes you need the dynamics lecture. If you go back and have a look at it, we actually had that thermal actuator at the very beginning that started to move at low frequencies, and then all of a sudden the dampings killed the vibration amplitude all the way until you saw resonance. So, even though the device was moving up and down, the movement at the output of your actuator was just so small that it became practically unusable. Frequency response is a similar matter, and power requirement, right? So do you need AC or DC? Do you need large voltages or not? Do you need large currents or not? Things like that are also important when you're choosing an actuator. So for time and frequency response of transducers, again, we saw that in the dynamics lecture. For a low Q system with high damping, you get this exponential rise at the output, and a slow system takes more time to respond. A fast system does it more quickly. The situation for MEMS devices is that you usually get a high Q system and you get ringing at the output of your device, and that is usually your concern. If you look at the frequency response of your device, again, for MEMS devices, you have a high Q, so you see a clear peak in the resonance response or in the spectrum of this device. Low frequencies where you usually use your device, the response is similar to your static response, and then very high frequencies, it's like any second order system. Now, if you look at this behavior here, and especially in case of actuators, you have to be a bit careful. You see that at low frequencies, we get some amplitude at the output of the system. Resonance, we get a larger signal, and high frequencies, the amplitude drops. So if your input signal changes like this, initially you have low frequencies, then you match the resonant frequency of the structure, and then the frequency goes up. This is how the output of your system will look like. Low frequencies, you get some amplitude. At resonance, you get Q times what you had earlier on, and very high frequencies, the device stops to respond essentially to your input. So basically, the output is too small. When you're dealing with actuators, it's important to keep this in mind. Now, what is calibration? Calibration is the process through which we make sure the device is telling us the truth, right? Essentially, we are trying to deal with accuracy problem. So we measure the output of the device and compare it to a standard. And it is a process through which we compensate for non-ideal physics that we may have, right? So it could be the asymmetries that we have in our circuit or on system. It could be geometric tolerances that we have or uncertainties that we have. It could be that the model that we have for the device is not accurate enough, right? So we basically have some unknown interferences or parasitics that have to be accounted for. And through calibration, we basically take a standard device that is trusted and compare the output of our system to that system for a given input, and then basically adjust the ratios or coefficients or offsets for our device. Note that calibration fixes accuracy issues but not precision, right? So you may still have a noisy output from your sensor, but at least if you average it out, it will be close to the true value. Calibration is very, very important when you're dealing with a new sensor. and you're especially developing a new sensor, because in many cases, until you test the device, you really don't know how much you could trust the models that you had for the device behavior. So you always have to have a reference to compare the sensor output to it. Now, in a microsystem, when we look at it, you have to put all of these things that we learned so far together. A lot of the micro devices that we have out there, a lot of the microsensors that we have out there, they embed in them an actuator. So what you have is a sensor structure that is monitoring a system response. For example, if you have an accelerometer, there is some acceleration, some inertial force that is applied to the device. You have a mechanical system that responds to that force. There is some signal conditioning that, for example, you linearize the sensor output, or you get rid of the offsets or things like that. And then you display that data, but then in order to keep everything nice and under control and linear, you usually have some feedback where you go and take the output, like, let's say if the proof mass of your accelerometer has displaced, you go and produce a signal internally to push it back to where it was. So you will have a closed loop system where you have signal conditioning and actuators and all sorts of system components inside that one tiny package that you see. So with the discussion on transduction, we're going to deal with the interface between your sensors and actuators and the real world. You already know how the device is made, the sensors and actuators are made. You already know a little bit about their dynamic and static responses. What we're going to learn over the next few lectures is how this interface with the real world works. How do we exchange information between our micromechanical system and whatever other outside parameter that is of interest to us. And then once we learn that part, we move into the signal conditioning and interfacing aspects. So that's that for this lecture video. We're going to talk about piezoresistive sensing as the first transduction method in the next video. Thank you.